Now we will see the solution about the traveling waves. In the past, there was two different approaches. One approach is reproducing not the real behavior and neither the amplitude with artificial pulse and limited number of reflection. Here on the left, we have a waveform with artificial pulse with a capacitor discharge. On the right, we have the real waveform, and we can see it's not the same. Using real-time simulator, we can reproduce the faithful waveform, but just in low level. They don't have power and then don't have current, just 10 volts peak to inject, and it's not the condition. And the IDs in the real life measure the complete real waveform. They measure at the secondary level, and the partial solutions will not represent the actual behavior of the ID. No, it's not the reality. Here we can see, here our simulation software, we have a Boolean lattice diagram too. Here it's an artificial waveform. You can see here the pulse on both sides. And here is an artificial waveform. And the next picture. Now we have the real waveform. Here we have a lot of reflection that can't be seen on the artificial condition. We can compare these two approaches that we have in the past using simulator and use pulse generator. About the simulation fidelity, using simulator, you use real waveform, and the pulse generation is not the real, it's artificial waveform. About the injection level, using the simulator, we have only 10 volts peak, but using, in the other hand, the pulse generation, you can inject secondary level. About the ID input, we cannot test the inputs because we have to bypass or use a modified ID for this test. With pulse generation is a good condition because you can test the ID inputs. About portability, using the simulator, usually big and heavy. On the other hand, we have pulse generation, it's lightweight. And to do tests on site, it's not a good idea to use the simulator, and it's best solution to use the pulse generation. About the investment, the simulator is a high investment, and pulse generation is best value for money. About contract file, we can deal with contract file with simulator, and pulse generation, you cannot. About to do sensitivity test, you can do sensitivity test with simulator because you can put a resistance and the waveform will be changed. And for the pulse generation, you cannot change, you cannot verify the sensitivity of the traveling wave. About the number of reflections, we can deal with several reflections on the simulator. On the pulse generation, is limited. And about the transmission line model of the traveling wave, use a frequency independent line model. Instead of the pulse generation, you use only based on traveling wave propagation time. We do not have the real mathematical model for the transmission line. And the question is, why not to test using the best of two solutions? Think about this. We developed CTW1 that you can inject the real waveform with secondary level. You can test the ID input. It's lightweight. You can carry it to test on site. It's best value for money. You can deal with contract file. You can import contract file to inject. We can simulate and export the contract file to import and playback in the ID. We can do sensitive tests. We can deal with several reflections and use the frequency dependent line model for the test. Here, it's about how the tool works. It's a software and hardware together, and use the principle of superposition. We use the test set with kilohertz, that's this one, and the traveling wave model that use this one. With the simulated signal, it's used to inject in the test set the high frequency, and the traveling the wave, the low frequency. In the traveling wave, we will inject the high frequency, and then with parallel of the current and the serial of the voltage, we have together on the ID input, the device under test, we have the sum of these two signs. Here we have on the left the calculated sign, and here it was capture the real waveform, and that was the same conditions. Here there are some setups that we already done test with different manufacturer of the IDs for location, for protection, and some labs that have our equipment. Now I want to show to you some case studies. Here, one case study for fault location, this condition. We model on our PS Symbol software, changing the fault type, fault location, incident angle, submitted 57 test scenarios, repeating this scenario 3 times, each one, totalizing 171, injecting in 3 differential commercial IDs, totalizing 513 tests. Here we have the model of frequency-dependent transmission line, the circuit breaker model, the CT and VT model, the busbar capacitance, and everything. Here it's one example of fault A to ground with 35% of location and 30 degrees. Here we have the voltage up, and here the current. With a zoom, we can see here all the high frequency of the signal that was simulated and is injected with the hardware. Here there are the results. On the horizontal axis, we have the fault location in percentage, and the vertical axis, we have the error in meters. In blue, we have the ID A, in red, the ID letter B, in the green color, the ID letter C. And here is the result for BC to ground fault and ABC fault. We can see here almost all the test accuracy is less than 0.15% of error of all manufacturers and IDs. Here, the IDB, we compare the errors in meters, doing the location with impedance with Z, and the traveling wave. We have here the traveling wave error, it's very, very low, and we have the impedance location up to 1.4 kilometers errors. Now we have the case study 2 that was done to verify the protection. Now we verify the protection using the traveling wave. It was running 76 test scenario, changing the fault type, fault location, incident angle too, and it was repeated 3 times each one. It was 2,028 tests with the commercial IDs. Here, the Schweitzer ID, the transmission line with 100 kilometers. Here, the waveforms, one substation, the other substation. Here we have comparing the zone 1 21 traditional distance and the time of the traveling wave trip time. Here comparing on the horizontal axis the fault location, and the vertical axis is now the trip time of the protection. In red and blue, we have a very, very low trip time for traveling wave. And here in green and purple, we have the trip time for zone 1 distance protection. And here we have up to less than 10 milliseconds when the fault is very near, and it's up to 20 something milliseconds when it's come too far away. Another type of test, the BC ground, we have the same behavior, and BC fault, single phase, double phase fault, and the three-phase fault. Here the results. Verifying the statistical analysis of these results, we have the average of 12 milliseconds for the 21 protection, and we have the average of 0.9 milliseconds for the traveling wave protection, and we have up to near to 600 microseconds of the trip time of traveling wave. Here we have the trip time comparing for the fault location. We have the propagation time, and here we have a little difference. If it's far away for the terminal, we change a little here, some microseconds. It's very, very low because the propagation time of the transmission line. The conclusion of this study, it was 741 contingent scenarios, most error less than 0.15%. The fault location travel wave was in the order of meters, and in the impedance up to kilometers. We have trip time less than 1 millisecond, up to 6 microseconds. The trip time was captured. Here we show the importance of testing the ID in condition close to the real, and the PSMO used the reliable models with realistic waveforms, and the CTW was showing a powerful tool with secondary level and megahertz condition to inject.